Hello, everybody. It is my pleasure to present at the 13th International Conference on Mathematical Modeling and Physical Sciences in Greece. And I'm going to present the work made by the DropletDynamics group at the International Center for Numerical Methods and Engineering of Polytechnic University of Catalonia in Spain. And our work is devoted to enriched finite element level set, conservative level set approach for microfluidic two-phase flows. And I will also mention something about peculiarities of the flows with contact lines. So we are a research group in Barcelona, Spain, working on microfluidics. One of our main applications, applications of interest is inkjet printing, because as you probably know, inkjet printing has gone far beyond its original application as a means of graphical or text printing, and is used as an advanced manufacturing technique whenever you would like to produce a very well-defined circuit or very well-defined thin object. So it's used in the optoelectronics, in bioprinting, and many other applications. So in those applications, it's very important to be able to produce perfect droplets. Okay, so usually these things are printed using the so-called drop-on-demand printing. So you deposit droplet by droplet. So that's why our interest is the droplets. And for instance, you can see here a droplet coming out of the nozzle, one with the tail a little bit deformed, and then a perfect droplet. So we'd like to study how we can produce the perfect droplets. At our institution, we have an experimental setup, and one division of our group is working hard on applying data-driven methodologies in order to correlate the input and output parameter of printing devices. We have created quite a large database in order to use neural networks to find those correlations. There are some videos that we recorded, the outcomes of the printing depending on the input parameters. You can consult our database freely on the following link. But on many occasions, the experiments are not sufficient. In which sense? We cannot embrace with our experiments all the possible situations or all the possible ink properties, because we have limited access to the inks. So in those cases, and also in case you want to analyze some phenomena that are difficult to capture, such as impact of the droplet against substrate, we have to also go for the CFD simulations. And my talk here will be about the CFD simulations when we want to model our droplet ejection or droplet flight or droplet impact over the substrate using the traditional computational approaches. So traditional in the sense of non-data driven. So we have proposed enriched stabilized finite element method for dealing with the two-phase flows. I will speak about it, but the main goal of this method is to capture exactly or very accurately the discontinuities at the liquid-gas interface. And as we know, in the microfluidics, surface tension plays a major role. So you have both discontinuities in the pressure gradient due to the change of the density and the jump in the pressure due to the presence of surface tension. So unlike the typical approach, continuum surface approach, where the surface tension is spread at a finite width interface, we managed to really model the surface tension related effects on an infinitely thin boundary. So our goal is not only to represent the discontinuities very well, but also to convect or capture the evolution of the interface very well. And my talk will concentrate on how we can equip the enriched finite element method with the type of level set methodology that will allow us to have very good mass and shape conservation. So our governing equations are the Navier-Stokes equations, equipped with the Dirichlet and Neumann boundary conditions, and the peculiar feature that we have in microfluidics is this term over here, where we have the jump and the stress that is proportional to the surface tension coefficient and the curvature. So we see it here. So when we want to do the variational formulation, we can write it as follows. The interesting thing is that the surface tension related term will have to be treated with lots of care, because one thing is the curvature of the droplet, of a free droplet, and the other thing is the curvature in the presence of contact with solid, where we have the contact line. So, but we will speak about it a bit later. Okay, in order to represent the position of the two-phase interface, we use the level set approach. Basically the distance function, which is has a negative sign on one side of the interface and positive on the other one. And in order to be able to compute accurately the terms that enter our governing equations in the elements that are cut by the interface, we perform the so-called tetrahedral splitting. So we create some elements, but most importantly, in order to be able to capture accurately the discontinuity, we perform the finite element enrichment. As you know, the standard finite element shape functions can only represent continuous variations, and we have here the pressure jumps, weak and strong discontinuities in the pressure, means pressure and pressure gradient. So we have proposed a set of enrichment functions that allow us to represent intra-elemental discontinuities. You can refer to these references for the details on the functions. But the very important aspect is that once we have represented the discontinuity, we perform the static condensation of the additional degrees of freedom associated to these functions. That's why we call our method an enriched finite element method and not extended finite element method, because we actually condense these functions. So finally, when we assemble our total system of equations, we don't have any additional degrees of freedom. So we condense them. So we represent the discontinuity, we add the contributions corresponding to these additional shape functions, and then we condense them. Okay, and this works pretty fine. So we can really represent strong discontinuities, very large density ratios, already on the coarse meshes. We don't need to refine mesh next to the interface because we have the enriched shape functions. However, we need to convect our interface. We need to track the interface, capture evolution of the interface. And if we apply, and that's what we did in the beginning, the classical level set method, which is basically a signed distance function, which is shown here. After some time, this distance function starts losing its property of the distance, and also it leads to shape deviations. It can diffuse, and also most importantly, it leads to severe mass loss unless redistancing is employed. And redistancing, when you bring back the level set function to become a distance function, is a costly procedure, and also it's a kind of ad hoc strategy to deal with this. Okay, so typically if you use traditional level set, you have to do redistancing and also typically smoothing, because it loses its smoothness often. So in order to tackle this problem, we have followed the idea proposed originally by Olson and Price back in 2005, where they said that a good idea of capturing the interface evolution is not to use the distance function, which is shown here, but to use a smooth Heaviside function that is shown over here. If we didn't have numerical issues of using an exact Heaviside function, we would have been exactly having absolutely zero mass loss. If we smooth it, we will have a controlled mass loss, because this function variation will be only restricted to a very narrow region next to the interface. So this smooth Heaviside function can be approximated by the following formula, and that's what we employ. However, even if you start moving this smooth Heaviside function instead of our original distance function, after some time it will start losing its steepness. It will become also, it will start inclining, and this will lead to the problems that we already faced with the traditional level set. In order to tackle this issue, the authors I mentioned have proposed to solve a special equation, which is shown here, evolution equation that is shown over here, that actually has the effect of sharpening. So if your smooth heaviside functions or if your interface stretch somewhere, solving this equation over here will compress it back. If somewhere it compressed too much, it will stretch it back. So we call this a sharpening equation. This equation you see over here has also a diffusive term, which is added there for the numerical purposes to ensure the stability. This equation, if you play around with it a little bit, you can separate it in several terms, and it can be viewed as a pseudo-convection diffusion reaction equation. So this sharpening equation is a pseudo-convection diffusion reaction equation, has the shape of convection diffusion reaction, but these terms don't have the physical meaning of convection diffusion and reaction. So we can rewrite it in the following way. It is very advantageous to write it in this way, because if you have a standard convection diffusion reaction code, you simply can recall the coefficients and be able to use this sharpening equation without too much of implementation effort. Okay, so this equation is must be solved until reaching the steady state, and once the steady state is reached to the given accuracy, this means that the original smooth heaviside function is recovered. Once again, what is the main advantage of our combination of conservative level set with our enriched finite element? Conservative level set also has some issues with the computation of normals far away from the interface. But for us, since we are representing the discontinuity exactly over the cut elements, we actually do not care what's happening far away from the interface. So we don't spread the surface tension over a finite region. We have everything exactly on this zero thickness, and we only care about having our interface and the normals just at the interface and maybe just the adjacent element. Moreover, the pseudo-convection diffusion reaction or sharpening equation does not need to be solved in the entire domain. We can just choose an area in the vicinity of the interface and solve it there. Thus, solving this equation does not increase considerably the computational cost. So here I show a window where I truncate and I solve this equation only in the vicinity of the interface. So this is the algorithm. Let me just show you a video which shows that solving sharpening equation, you can even start not with the heaviside function, even if you start with this linear function, steady state solution leads to recovery of the function that we want to obtain. But in practice, we give in the initialization step already this function, and then we convect and only recover it when it gets stretched or compressed. This is an example, 1D example, where we have a straight interface, and we submit this domain to a non-zero strain velocity field. Okay, so there is some stretching. So if you apply the methodology without sharpening and start convecting it, you will see that the level set function will start losing its steepness. Okay, you can see it here already after some time steps. And this here, the figure on the right, shows that if you apply the sharpening, then the interface function, then this level set function remains intact. Next, we solve here the famous Levesque type test. Okay, we solve it here in 2D. So we prescribe a given velocity field. We see how our originally circular drop deforms, and after some periods, it goes back to its original configuration, and we can see that application of the conventional level set, in this case on this mesh, led to 12, nearly 13% of mass loss, while conservative level set in the implementation I've shown considerably improves it. It improves it 100 times. Next, classical bubble rising example. Here also with an unarmed eye, you can see that the conservative level set conserves mass very well. Here there is a graph that shows that one has to be careful when choosing the narrow band around the interface where sharpening equation is solved. If you choose it too small, you might start losing mass, but if you choose it well, you conserve mass very, very accurately. This is a three-dimensional example, as you can see, we can obtain very nice results already on such coarse meshes. We don't, as you see, we don't refine anywhere at the interface, and this is thanks to our enriched finite element approach, which does not require for any mesh refinement to accurately capture the sharp discontinuity. Here you can see how the ISO lines are conserved with the droplet falling and rising bubble example. You can see that it's preserved very well. And as you probably remember, the talk was called two-phase approach with contact lines, for multi-phase flows with contact lines. So let me just give a little comment, because it's really important if you have contact with solid. So by now we saw all the examples where the droplets were free, so they were moving in the air. What happens if you have a contact line? So apparently, you remember there was the diffusive term that if you use linear elements, you have to integrate by parts. So theoretically, or if you treat it exactly, you should have a boundary term that appears here. So this boundary term would mean a normal flux, normal pseudo heat flux at the interface. If you have a contact line and you want to preserve the contact angle, which value of this term should you set? You know, when you have a free droplet, this term vanishes. It's not there because we don't have it. But if you have it, if you are in contact with solid, you don't actually know what to set this term to. And if you just omit it, which means that you say that it's 0, what will happen is what you can see here. Here you should have a 60-degree contact angle. This is, for instance, the situation. But after some time, your simulation will start bringing this angle to 90 degrees. And that's definitely not what you want to get. So what we have learned is that the way of tackling it, and this was also mentioned by Olson, is that it makes sense not only to integrate by parts the diffusive term, which is mandatory because it says we have here second derivatives, and otherwise we cannot deal with it when creating the weak form, but also our convective term. So an alternative is, instead of interpreting the sharpening equation as the convection diffusion reaction equation, is to interpret it as a convection diffusion equation, keep the terms that we've previously separated into convection and reaction as one single term, and then do the weak form, or then write the variational form, and then integrate by parts also this new convective term. If you do so, then you will have a boundary term which involves, on one hand side, this pseudo-convective flux, and this pseudo-diffusive flux. As was shown in the original work I mentioned, the sum of these terms, setting the sum of these two terms to 0, meaning that there is neither, so the convective and diffusive fluxes at the boundary compensate each other, allows us to perfectly preserve the contact angle. So if you see the solution on the right, where we once again want to maintain our 60 degrees contact angle in two examples, and we can see that it's perfectly maintained. So this is, I'm sorry, I'm slightly beyond time. So we saw that combining the enriched finite elements with the conservative level set is a promising approach. We can get a very approach with a very nice conservation properties. We don't need to spend lots of computational time to keep our distance function intact. We saw it on the limited band. One has to be careful when dealing with the terms stemming out from the integration by parts. Particularly, one has to be careful with the terms related to the contact with solid. And the most important message is that with our approach, everything is fine and accurate next to the interface in terms of geometry. We don't care about the rest. And this is a very, I believe this is a very important advantage over many of the nice modern approaches, which nevertheless require to keep the regularity of everything in the whole domain. So we can deal with our discontinuities in the cut elements, and we want to preserve nicely only the things at the interface. So these are some of our works. Please, you are welcome to come and see some of our developments in our website, DropletCIMNE.com. And if you have any questions or recommendations, we would be happy to answer them. Thank you very much for your attention.